MATLAB kernel. It's called iMATLAB. I think it's supposed to be more robust with updated versions of MATLAB.
Can you install with kernel?
You can install it the same way, so instead of MATLAB kernel, you write install iMATLAB. It's made by the same people.
Oh, really? Okay.
So should I start, or am I waiting for people to install things? Yeah. I don't know how long this is going to take. Basically, the entire data set that I talked about, the Sherlock data set, is available. You've downloaded the tutorial that contains ROI data already, like in the directory structure that the tutorial will show you how to create. But you could also download the whole brain data in Nifty format, and this first section of the tutorial, this unpacking part, takes you from the Nifty format into the directory structure and MATLAB format files, which are smaller and in a different shape. So if you wanted the original whole brain data, well, the pre-processed whole brain data, you would go here. This is big, though, so I didn't want to ask everyone to download it for this tutorial. And then if you want the whole brain data set in the MATLAB format that would go with this tutorial, you can download it here from DataLad. So maybe for hackathon purposes, you'll want that. Okay, so the way that this works, I'm in the How to Use Sherlock Nifty Kit file, which is at the top level. And I'll just kind of show you the overall directory structure. So I actually keep all my experiments in the same directory structure, and I find it useful to be able to, even for my students who use Python, I still have every data set on my server set up in the same structure, so I can go and look at stuff, and then we do things in parallel sometimes. Or some people just use this. And it's nice for being able to compare. You know, we have a lot of open data sets now of different auditory narrative and movie stimuli and even recall, and so it's nice to be able to concatenate a lot of that stuff. And I see a future of trying to generalize across many different data sets. Let's see, so you have your code in here. Nifty Tools is a toolbox that it's developed at Rotman. It's just for loading Nifty files into MATLAB and doing a couple of things. We only use like 3 of these functions, but it's a nice little toolbox that is available on the MATLAB Central File Exchange. And then in standard, I keep brain anatomical images and ROIs, and these ROIs are just Nifty images filled with zeros and then ones, like where the ROI is. That's it. This is 3 millimeter MNI space. And we have the MNI 3 millimeter brain and a mask of just the entire brain, as well as let's see, auditory. Odd early is one of the ROIs that you already have data for. So this is early auditory cortex, but it's kind of a big ROI. It includes not just A1, but some other, probably low-level language areas too. And it's defined functionally, actually, from inter-subject correlation in an auditory narrative, and just kind of restricting it to Heschel-Starrus. A1 reverse is functionally defined from reverse speech. So it's the inter-subject correlation when subjects are listening to a narrative that's been flipped temporally. So there's still like volume, there's still like sound information, but there's nothing that's really language. And then we have a couple of other ROIs. The MPFC is from a resting state atlas. Early visual is defined functionally, just high correlations, high inter-subject correlations in the kind of V1 vicinity. It's not very exact. And then posterior medial cortex. This is really more like PCC, actually. It's also functionally defined from resting state in an atlas. And posterior perihippocampal cortex. Okay, so those are ROIs you could play around with. If you want more, I have a ton more. You just ask me. Any region that you think you might want to work on, I can see if I have one in my library somewhere. Okay, so the subjects, there's 17 subjects, and each one of these subject directories, you have your movie data and your recall data. So the movie data is already aligned across subjects, and you would expect it to be temporally aligned from the stimulus because they all saw the same movie, but it's also aligned, you know, in case like the movie started a bit later or a bit earlier for various reasons in different subjects, that's been taken care of. And that would have happened if, you know, we were doing eye tracking for these subjects. So if the eye tracker like wasn't working, then we would skip calibration, and so it might actually come from a different, slightly different time in the original data. But I think that's all been taken care of here.
All from the HRF, right?
All subjects are shifted 3 TRs to count for the HRF. And the way that we determine that, 3 TRs is 4.5 seconds. And we determine that by looking at we take the auditory envelope of the stimulus, and then we take the response in early auditory cortex, and then we do a cross correlation and find the peak match. I'll show you the cross correlation step anyway. So that's how we chose the delay, although it's pretty standard delay. But if you have your own data, I recommend you do it that way. And then, okay, so for each subject, if you had unpacked the whole brain data, then the whole brain data would be here. So these are ROI files, but you would have, the whole brain data nifty would be here, and then the unpacking cell would then turn it into a MATLAB structure. The recall data is not aligned across subjects because there's no stimulus, and it's just whenever they happen to say anything. And so part of what the tutorial will show is how we load in the event times and then do the analysis individually for each subject. Okay. And these are the event times here for all of the subjects, and then this is a labels file. I'll show you. This is a hand-made labels file where for every one of 1,000 segments in Sherlock, there's a detailed description of what's happening at that moment. So this is every couple of seconds, basically, somebody has gone in and written what's happening. And then labels are over here. So you have, some of these are objective and some are subjective, right? So indoor versus outdoor is pretty objective. You just say like what's happening on the screen and which characters are on the screen, who's the focus of the shot, who's talking, the location. The location turns out to be not a very useful label because in this movie they almost never go back to the same place. Yeah. The camera angle, we never use this for anything. Whether there's music or not. Words on the screen. So that happens quite a bit in Sherlock because he's always texting, and then they have like text pop up on the screen for you to read. And then 4 different raters that said they rated arousal and valence for every moment of the movie. And arousal is on a scale of 1 to 5. Valence is they had to choose positive or negative. There's no neutral allowed. Okay. Mm-hmm.
When you showed that figure of classification accuracy for time segments with the number of features, do you remember which combination of features led to the peak performance?
Yes. Let me just show you I can show you the supplement here. Actually, maybe I can. Uh-oh. Okay, so this is what you're talking about, right? What you can do is rank them here. So this predictor ranking goes with this classifier accuracy plot, right? So speaking is the best predictor, at least for this region. In a lot of other regions I've looked, speaking is also a very good predictor, though. And of course, speaking is highly correlated with Sherlock being on the screen. So that might be one of the reasons that Sherlock isn't as important in this list, right? So anytime that you have these correlated predictors, like one of them is going to take up a lot of the variance, and then the other one kind of gets pushed down. The number of locations is the next best predictor. Arousal, written words, valence, and then Sherlock is in here, but after that, adding more labels doesn't seem to improve performance anymore, at least in this region. And we have yet to actually test this everywhere. So you would expect to see something like in, PPA, then maybe location-relevant features would dominate as opposed to some of these other features. But that is that's the approach. Okay, let's get into it here. You'll have to set the path for your own computer in order to be able to follow along if you have MATLAB. I'm going to skip unpacking because we don't have the original nifty data to unpack. If you do this yourself, it will take a while though, so just be prepared for that. This first cell calculates the ROI time courses. So what this function does is it loads the whole brain data for each individual subject, and it loads the ROI, and it cuts out the data from the ROI on the functional, the voxels by time matrix, and stores it. So can I actually open it here? Okay. Right. So it goes to the movie data and to the recall data. It loads the whole brain data. Okay, loads the ROI. If your data, if your whole brain data are a nifty format, then it takes this opportunity to resave them as a .mat file, which is a lot smaller and quicker to load. So in the future, we'll always check for both and load the .mat if it exists. It reshapes if it's nifty data, it reshapes it into voxels by time, because the nifty data will be the 3D volume by time. And then it cuts out the portion of the data that corresponds to the ROI that you're working on. It saves an uncropped version of that, meaning that there is a way to run this tutorial where the data isn't, like all of the timing isn't already taken care of, so you would have to say when the stimulus began for each subject. And then it wants to save versions that do have that information already taken into account and don't. And then once the ROI data are saved for each subject, then it's a lot faster to do analyses on the ROIs. That's why we have that step. So, you could imagine doing all of your analyses, loading the whole brain data for every subject every time you do everything, and that would be really painful. But it turns out that most of the stuff that you do that you want to be nimble about is at the ROI level. So what this cell does is create these files. Okay, so we can look at one of them. Okay, so we have the R data is the ROI data. So in this case, it's the early auditory cortex bilateral. It's a 1,018 voxels and 1,976 time points. So that's the 50 minutes. The original movie data was in 2 scans, so just because we didn't know at that time whether we were going to be able to run the scanner for 50 minutes straight. So we collected in 2 scans, but they're immediately back to back. And so this data set that you have, they're already cropped and concatenated together, but originally it is 2 different scans. So the total time is 1,976 TRs. And then the kept voxels, the reason that we have this kept voxels vector is a bit legacy, and I'm not sure how much of it is still in the original tutorial. But, well, so the reason is that when you're doing intersubject correlation analyses, you have dropout in your signal, and that dropout is different for every person because the brain is in a different place relative to the coil. And so the way if you have dropout in too many of your subjects for a particular region, you don't want to include that in your intersubject correlation map. And so you want to know for every subject which voxels actually had signal in them, and you want to carry that information forward as you go on to make your group level maps. So the way that we would do this, the way that I would recommend doing this in general is you make a mean image of your functional data, and then you plot a histogram of all of the voxel values. And so the actual magnitude of those values will vary from scanner to scanner. It's a completely arbitrary number. It'll be, I've seen it be in the hundreds, and I've seen it be in the thousands. The range varies too. Those are the luminance values, right? So if you plot a histogram of that, you're going to see a big spike of stuff at 0 or around 0, which is all of the voxels that are outside of the brain, and they have no signal. And then you'll see kind of, normal-ish looking distribution that is the luminance values inside of the brain. And then you want to pick a threshold that's kind of at the bottom of that distribution. Then if you go back and look at your functional image overlaid on the anatomical image, you'll see that that's where the brain is. That's like basically where the skull is. So that's how you should threshold your data. I don't know how that's handled in like standard fMRI analysis packages, actually.
So people are using Python. They have the Nyler library has a compute API mask that does the percentile threshold.
It does. Okay, great. Cool. Okay, and we can just look at what's in the ROI data here for auditory cortex. Here. All right, and you see these kind of you can see that. It looks kind of blocky, like inrows, because of the way that the three-dimensional ROI was unwrapped into this two-dimensional, the y-axis here, right? But you can also see that all of the voxels kind of share this fluctuation over time. These vertical stripes are showing you that a lot of the voxels in this ROI are doing roughly the same thing over time. And that's often, the reason that you would choose an ROI in the first place is you think that there's some reason for grouping all of those voxels together. They have some kind of functional property that they share. So in this next cell, we can do some plotting of the time courses for this ROI. Okay, so we're going to... Yeah.
Has the data, have the ROIs been demeaned?
I think, in the part that was in the GitHub repo, they're already demeaned. There is a step in one of these functions that also enforces that. But I can't remember if I think that the Princeton data space Nifty files have not been demeaned, so you could look at that distribution I was talking about. The data lab one, I don't know. Yeah.
I guess this is a practical point, very boring methodological point, but if you take a typical ROI and you correlate any two time points, they're going to be very correlated because the voxels have different means from each other. And so, one voxel's mean is 1,000 units, and the other voxel's mean is 1,200 units. The variance is only around 10 or 15 or whatever, right? So regardless of whether a voxel is up or down, it's still going to be lower than its neighbor that has a higher mean. And so when you do a correlation of two moments in time, the relative ordering of the high voxels and the low voxels just never changes, right? So all time points are correlated with each other. So one of the things you have to do is you have to take each voxel and remove its mean before you do any of the pattern correlations.
Yeah, that's right. And that line is here in the Nifty ROI Time Course code, the Z-score. But often we'll just do that as a very first step at every voxel in the brain before we even do any ROI stuff. Yeah. So if we calculate the time-time correlation of this Yeah, you can see it's been z-scored here too in the values. If we calculate this time-time correlation matrix, then the average value of the matrix will be 0. But if you were to do that on the original un-z-scored data, then all of the correlations between time points would be like 0.99. Yeah.
There's another point here, which is, do you mind if I?
Yeah.
So like, how many people here are familiar with the debate about global signal regression and fMRI? Familiar with it, right? So the problem is that if you do functional connectivity analysis, you're correlating, you're taking a time correlation of two different spatial locations. And if you don't remove the global signal in fMRI, all the spatial locations share a signal. And so all the correlations are super high. These are temporal correlations. So what people do is they remove the global mean. So you're averaging across space, across the whole brain, and you get an average time course. And then you subtract it out or you project it out. And people who are familiar with this debate will be aware that there's a problem with that, which is that removing the mean over time, removing the spatial mean, removing that time course, guarantees that when you take correlations from some pairs of regions, you will have to get anti-correlations. The positive and negative correlations have to kind of balance out in some way. And this is why there was this huge debate about when the default mode network is up and the, what's it called? Frontoparietal network is down.
Test positive.
Yeah, okay. Anyway, so that the logic behind that crops up again here. Because here, when you demean individual ROIs, remove the mean from each voxel, you are now taking the mean over time, and when you do, so your mean is across time rather than across the whole brain. When you do correlations, you're doing correlations across time points of the spatial pattern. It's actually the exact dual of the functional connectivity global signal regression thing. It's the same problem. So what that means is, whereas the global mean regression in functional connectivity produces anti-correlations, like anti-functional connectivity, what this will produce is negative correlations between the patterns. It means if you're going to have a certain pattern that's correlated between two time points, you have to have another pattern that's anti-correlated. So when you do the time-time correlation patterns, you will see negative correlation. It doesn't mean necessarily that the brain is truly expressing a negative pattern. It could be, but this pre-processing step, which we kind of need to do in the same way, is introducing the same issue. Yeah.
So what happens if you just z-score or demean within voxel time series?
That's what we do.
That is what you
Yeah.
do.
So you lose the relative means to each voxel. Does that matter to where we can rate?
So you kind of have to remove the mean from each voxel, and once you've done that, your subsequent analysis is going to be taking two time points and you're going to correlate the patterns. Before you remove the mean, those two things were independent in time. But the mean is over time, which means that information from all time points is inserted into every time point. Does that make sense? So that's the same logic.
I think you could demean with respect to a voxel's own mean over time versus the average of all the voxel's means over time.
So if you do every voxel individually over time, that does produce this problem. The other way to think about it is removing the mean of each voxel from every voxel is the same as removing the mean of the spatial pattern from the spatial pattern. That is the same. Anyway, I know. You mind if I just draw this on the
Yeah,
board?
this is a pretty hard concept to do without visuals. I like what we actually do in this data is we remove the mean of every voxel individually, and what it's separate. But Chris is saying that it does not really mean that they're independent. Like we're calculating the mean of each voxel, but then when we're doing pattern analysis by correlating patterns that are at different time points, that go ahead.
Okay, so you have a bunch of data in a box, and then you get a time course. So this is the mean, is this, and here would be the mean is this. Okay. When you do functional connectivity You're taking one ROI and another ROI, and you correlate them. That's what function connectivity is. If you've already removed the global signal, which is this, from each voxel, this correlation is confounded because some of these correlations have to be negative if others are positive. Now, what we're doing now is this. We're in an ROI. We are computing two different time points and correlating them. But we've removed out this thing. It's exactly the same. Okay?
Yeah. The upshot is that when you have a time-time correlation matrix, so you're calculating pattern correlation between every pair of time points in your stimulus, you shouldn't take the absolute value of these correlations too seriously. That's the upshot. Because you've done this demeaning, and you kind of had to do it, that pushes around these correlation values, and some of them are now going to be negative. In the original data, all of them were positive, like 0.99. Now, half of them are negative. Like, it's a mathematical necessity of the way that the demeaning works. So if you take the average of this matrix, it'll be 0, or like almost exactly 0. So relative, like comparisons between different cells is where you want to be doing your analyses, not saying like this one's negative and I'm going to build a theory on that, or this one's positive. Is that fair?
Yes. One small final thing is that in the original global signal regression in the functional connectivity world, you wouldn't just subtract the mean, you would project it out, so you would fit the mean to every voxel and take the residual. That operation truly guarantees exactly balanced. It guarantees the positives and negatives perfectly cancel. This procedure, if you just subtract the mean, it doesn't perfectly guarantee they're cancelled, but it still pushes them around. You still can't interpret them.
You can't interpret absolute value.
Yeah. There's a paper in like just writing all of that down. Like I think a lot of, it's kind of like wisdom that's kind of percolating around in the field, and sometimes it seems like people already know that, and sometimes it seems to have never come up, and I don't know.
Yeah, there's been like 5 papers on this topic in functional connectivity. Like every 3 years, someone writes the paper again, and it gets better each time. But I don't think it's ever been written for the pairs of time points.
Yeah, it's mathematically identical. Okay, so now we're back here. We're plotting the ROI time courses for the movie data. So the ROI time course, what I mean by that is we just average over all of the voxels in that ROI to get a single time course. Okay, so this first section, okay, there's all of our 17 subjects, and the black line is the mean. So it's good to just always do this and like look at your data. We often see this kind of thing at the beginning. Maybe this is another methodological thing that I will return to after we do some real stuff in the tutorial. So it's nice to look at the ROI time courses. But what we also want to do in inter-subject correlation is see how well the subjects match each other, right? So this section gives you a little shorthand view of each subject's time course correlation with the average of all of the other subjects. So subject 1, 2, 3, 4, and this is 0 for each subject. Okay, so the axes are stacked horizontally. And this black line tells you that this is 50 TRs. So what's happened here is we took the time course for subject 1, and then we calculated the average of the time course for all of the remaining subjects, and then we calculated the correlation, and that's here. And then we shifted the time courses relative to each other 1 TR at a time in both directions. And so what you're looking for is a pretty sharp peak. The sharper the peak, the more kind of specific the correlation, or the match between the time courses is to that particular, to that moment, right? To that alignment, temporal alignment between subjects. And so even if you shift them by 1, the correlation starts to drop and drop and drop. You can do that for every subject, and so these will be the inter-subject correlation values up here, and then the sharpness of this gives you some confidence as to whether that correlation is a real thing, or whether, you know, if you saw like a bunch of other peaks that were the same size, like pretty nearby, you might say, well, that's, you know, it's not very strong correlation. It's not very good correlation. But one of the things that's happening here is that as you shift more and more, you're losing time points to actually do the calculation on, because you like cut off the excess time points, if that makes sense. You know, you have 2 time courses, they're the same length, but then as you shift them, there's ones hanging off the end that you have to throw away. So this will also become noisier as you get further away from 0, just because there are fewer time points. Okay, so that's kind of a quality assurance check. We can look at how it looks in the posterior medial cortex too. So an auditory cortex, you know, this is as good as it's gonna get, basically. Like, these are very high correlations. I think we found that this group size is about where intersubject correlation starts to plateau. So, you know, we should probably write a paper about that too. And because we're doing one versus the average others, the number of subjects does matter, right? So if you were doing this pairwise, so one subject compared to each other subject individually, then you don't expect the correlation value to go up as you increase the group size. But because we're doing one versus average others, it does go up. It's not that it can go to 1. You're still measuring the quality of the underlying signal. But if you only had like 4 subjects, you wouldn't expect it to be this high.
Do you find much systematic variation or at least individuation on the lags across, like how much one person might do a TR behind others in the time course for your autocorrelation or your
Are you saying that if a person tends to be a bit behind the group in one ROI, are they also behind in another ROI? I don't know the answer to that. I mean, I wouldn't want to compare auditory, and I wouldn't want to compare a low level and a high level region, I guess. So you would ask that question in like A1 and B1. Yeah, I don't know the answer. The way that we do this is we almost always just use early auditory cortex. Partly because we can also match that to the audio envelope of the stimulus, so it's really nice ground truth. And then people who are giving us a correlation of lower than around 0.2 just drop. But that's not, you know, that's like kind of arbitrary. Yeah.
So in theory, you could also try to compute like the noise ceiling type of metric by including the subject in the mean before you do the iterative thing to see what the fidelity of the
Including the subject themselves in the mean.
Yeah, so I think that's at least one approach in the sort of RSA world to doing the noise ceiling kind of computation. So because they're already included in the mean, then correlating themselves to the mean, which they contribute in theory, should give you the absolute performance you should be able to give given the fidelity of the signal itself.
I don't think that we have done stuff like that. Yeah.
It's not totally clear to me what is meant by the noise ceiling there.
Like, what's the highest theoretical correspondence you could ever observe across people if people were exhibiting actually the same thing in individual differences with just noise?
It's unclear to me why putting the subject in is a more accurate estimator than getting the subject out.
No, it's not a more accurate. It's just the it's a. I'm not an expert on noise ceiling, so I shouldn't capitalize on this, but they're contributing to the mean also, so there's a redundancy there.
Yeah, I guess I don't see the reason for it either. Like, you know that correlation is 1, so why are you including it? That's what I don't get.
Wait, I think the idea is that there's 2 different kinds of noise here. So the one idea would be that like one kind of noise would be between subject variability, and the other one would be measurement noise.
Right,
Is that the issue?
Yeah, you're right.
And then the noise ceiling is you remove between subject variability and you're left only with instrumental noise. Is that the?
It's right. Yeah. So then you could compute some metric of your observed correlation proportional to the, overestimated correlation, which should account for the measurement noise. Something like those.
Okay. Yeah. I don't think we've done that.
I mean, only by accident. It improves the correlation.
Yeah, right.
Okay, this posterior medial cortex.
I guess I have a really good question that builds on this idea of signals and noise. Is this something that you see in
I haven't systematically looked at how it varies between different scanners. We've collected data on 1, 2, 3, 4, 5 different scanners. And then this is what it looks like.
One analysis I've done on whenever I get talked to one users say if you do the, at least for an ROI, for the intersubject correlation on 2 different scanners, and it's like a point, if you do it, correlations overall the brain, it was like a 0.99 correlation. It was like astonishingly reliable for that particular analysis. Where some people aren't proof didn't believe it, that I did it right.
There's enough data out there now to start to really ask these questions properly, though, I think. There are a couple of stimuli that are really becoming used on many different scanners. So like PyMan, there's like 100 subjects in that data set across 3 different scanners, maybe more, plus an ECOG data set.
That might be the most accurate question too.
Yeah.
An easy one, very cool.
Yeah.
You got any question on Mark?
Yeah, I expected that the width of this correlation function was going to be a lot bigger for
Yeah. I agree with you. I actually noticed this myself recently. I was going over this with my postdoc Lisa, and we were surprised that this wasn't slower because in the paper that you showed, measures this exact same thing, this autocorrelation. I think so. This is like maybe also something that's worth like hacking. This ROI crosses the midline. And I'm wondering whether like that has something to do with it. If you look, the spatial autocorrelation results in the Balzano paper clearly show that there should be a wider signal here.
You can make a map of autocorrelation.
Yeah, that's what's in the Stevens 2013 paper is the temporal version, and then the Balzano is the spatial version, and they like. So I think that it's something about this ROI, but I'm not sure what. Yeah.
The relationship between the width of the autocorrelation function and the slope of the power spectrum is not as simple as it looks.
Okay.
So like for certain classes of functions, the wider autocorrelation function is just simply predicting a steeper slope, but the way the side lobes work actually matters. So like the Fourier transform of the autocorrelation function is the power spectrum, and that immediately tells you that the relationship is not simple, right? And that the side lobes matter. So I guess that could be going on here. So like if we could see the amount of ringing in the tails, that might matter. Yeah.
Okay, yeah.
There's one more question.
For the Sherlock, it was done on the Allegra scanner and the Skyra scanner.
Skyra.
Or it wasn't Allegra at all? Okay. And then another question is, some participants fall asleep, and it's hard to know when they fell asleep or if they did fall asleep.
These people were eye-tracked.
Okay.
Yeah.
If you didn't have eye track, do you guys ever just look at early visual areas to see when the correlation starts to go down?
We always have follow-up memory questions, so that's how I would answer that. Asi has a lot of experience with dealing with this. So we have detailed, when we're unable to use eye tracking, then we have detailed memory questionnaires to see if people fell asleep. But for the most part, I would just say that you should watch their eyes if you can. In a movie, I think, it depends on your stimulus. So in a movie, it's not that common for people to fall asleep, especially if they know they're going to have to do a memory test afterwards. They're going to pay attention. But for auditory stimuli, it can be kind of, especially depending on the narrator, it can kind of be tough for people to stay focused. So, and some people just fall asleep more easily than others. So we never had to resort to looking at the visual cortex signal to make sure that people hadn't fallen asleep. But it is something that you could do. I think that we did find in a very preliminary analysis of the people that did fall asleep, I kind of thought maybe their early auditory cortex, you wouldn't be able to tell because, who knows, when you're asleep, maybe your A1 is still responding to the sounds that you're hearing, but actually we could tell, right? And then we had some kind of ideas about it possibly being like thalamic, but that's an experiment yet to be done to encourage people to fall asleep while they're listening to stimulus.
There's a paper from Helmut Laufs and Enzo Tagliazucci from 4 years ago, where they trained a classifier. They trained a classifier using sleep staging and simultaneous EEG fMRI. Then they applied the classifier to resting fMRI data. And the classifier was very good. So I don't know whether they released it, but there's no reason it wouldn't work while you're listening to a movie. I mean, on its face, you could just try it, right? I think they released it.
And the result was?
The result was that 50% of subjects are in stage 1 sleep after 10 minutes in rest.
Yeah. Yep.
But there was variability across data sets. Because they had the 1,000 connectomes data set, and then they had broke it down by center, and some of the centers, everyone was asleep after 5 minutes. Maybe they're medical students or something. But then some of that centers had very low sleep rates. Anyway, so that classifier might be out there. If that's
yeah, that could be very useful.
Built in, I can't remember if it was the WashU group or the.
I think it was the. I thought there was something that.
one.
Yeah. Child line. Because so OHB, there's a similar sort of thing this year. They talked about the one. There's a camera project with a few other people, and so they train. They basically do an eye tracking calibration effectively in the scanner, and then train it based on just signal from the eye. And you get a 0.97 correlation with an actual eye tracker, and then they apply it to. There's a preprint that they just applied to movies. I don't remember what the result is, or the authors, so I'm not helpful. But
That's great. Stephen Shepard was trying to do that a while ago, and I'm pleased to hear that somebody actually did it. Yeah. I'm surprised that it works that well too.
Yeah. So it doesn't. It's just a normal inbore camera rather than a.
No, it's just using the bowl from the on the
it's like
eye.
Yeah.
It's the ball
Yeah.
on the eye.
But the trick is not to use the brain; is to use the eyeballs.
Okay.
And then it's a 2-minute scan. You can just add any sequence. Yeah. And so you just have.
Oh, you train it in the.
You just have to sort of fixate, and you just build a classifier to decode the location. Yeah.
How precise is it? Yeah.
I just know it's it responds to tracks with an actual eye tracker incredibly well.
Pretty cool. I mean, I guess the temporal resolution can't be more than your TR. Okay, so some things to play around with there. Here are the time pattern correlations. Okay, so again, this is each subject, the correlation with the average of all of the other subjects. But now, instead of using their time courses, we're taking the pattern of activity in the ROI at any given time point, and we're calculating the correlation across subjects at that every pair of time points, each subject compared to the average others across all of the subjects. So this diagonal that you see is telling you that there's a similarity between different subjects at the corresponding time point in this ROI. But you see a lot of stuff off of the diagonal too. So this is in posterior medial cortex. This very well could be related to the fact that there's similar content between different time points in the movie, right? So if you also had a maybe human rated similarity, or in the case of this data set, Kieran Votrahali has a paper where he used Word2Vec to calculate similarity between all of the different time points in Sherlock, and then he's able to predict brain activity from the similarity between the descriptions of the different time points.
Is there a question over there?
Have you worried at all about the subject-to-subject differences in the number of voxels in an ROI?
Well, these ROIs are the same across all subjects.
Oh, right.
Yeah, they're not functionally defined. They're atlas. Yeah. So it depends on point-to-point correspondence between subjects. So you depend on the anatomical co-registration for this. But you can do functional co-registration as well with hyperalignment or SRM, and then you'll drastically improve your classification performance, if that is your goal. Okay, here's a function that plots the recall behavior. So these are the diagrams I was showing in my talk where I should put axis labels on these, sorry. The y-axis is time during the movie, and the x-axis is time during recall. So for this is our best subject from Sherlock. She hit like basically every single movie scene, and if I were to show you like smaller scene segmentations, which we have, you would also see like tiny little ones inside here where she's going through. Yeah, we're recoding the Sherlock events. Right now there are 50 events, and that was the work of one writer, who just kind of picked the biggest events that he thought, like the director's cuts. But there is variability across subjects in terms of where they place those event boundaries. There's a lot of variability, actually. So, and you could even ask, like, what's real about it? It's a subjective thing, like where those event boundaries are, how strong they are. So we're going back through it and having multiple people do the boundary ratings, having them rate how strong they think each boundary is, like looking at the different windows of how close the boundaries are to each other. And I think it's not right to treat it as like a categorical thing. Like it has a distribution, the event boundary. Okay, this cell, oh.
It looks like some subjects are spending a little bit longer to recall a movie segment than to watch it. Like I was just looking at the matrix for subject 1, and it seems that the rectangles are a little bit wider. Do you think it's like, it would be interesting to kind of formalize the subjects who spend a lot more time recalling segments?
Yeah, so one thing that varies a lot across people is how fast they talk also, by a factor of 2, actually. So we'd have to go back here and find out what they said and whether there was actually just a lot of pausing during this scene. That is one of the, from my talk earlier, one of the things we're doing is going sentence by sentence and seeing what kind of content there is in people's recalls. But yeah, even when you take a closer look at the behavior too, one thing you see is like even this entire block that got classified as categorized as a single scene's description, if you went sentence by sentence, you might actually decide that some of those sentences refer to the previous scene or the next scene. It's not always like as coherent as that. But as a course pass, you're like, oh yeah, it all seems like it's in that scene. So all of those questions have to be answered with a more careful treatment of the behavior.
Have you guys looked at differences, like if there's pauses from what the pattern is when they're paused versus when they're talking?
Not in Sherlock. There's not that many pauses in Sherlock. Yeah, the film festival data are designed for that purpose. And I don't know the answer. I think that if they're still within one scene, I don't even know how many pauses there really are that are inside a single movie description, but yeah. I mean, and they're going to be, if there are pauses, they're not going to be long enough to make a lot of claims about them thinking about something other than this particular scene, because the autocorrelation function is kind of large. Okay, so here we're going to calculate the average voxel pattern for each scene. And we'll do it in posterior medial cortex. So this is the first time we're introducing the recall data. So the movie data are time aligned for all of the subjects, but the recall data aren't. And that means that we have to load the event times. So the event times for the movie are the same for every subject, but the event times for recall are different for every subject, right? So that will be, let's see, let's just do this part of it. So this struct has the times for every subject. And if you look in here, So you'll see, as I said, the movie is actually split originally into two pieces, so those are separated here. So these are the start and stop times in TRs of each scene that the subject recalled. And then this is the second half of the movie. And then these are the start and stop times during the recall data for each of those scenes. And if you look at this field, you see the numbers 1 through 50 of the scenes that that person recalled. So we're going to use these start and stop times to go to the brain data for the movie and for the recall, pull out the scene, pull out one scene at a time, and then create an average value for each scene for every voxel in the ROI. Okay. And now we've, here we're calculating correlations within and between subjects in 4 different ways. These two are very similar. So this is the reinstatement analysis, basically. Within an individual subject, we're comparing each movie scene to its corresponding recalled scene, just for that person. So you calculate the pairwise correlation of all movie scenes and all recall scenes and take the diagonal of that matrix. I'll show you what that looks like a little more in the next step. And there are 2 ways that this is done. So sometimes people return to the same event during their recall. It doesn't happen a lot in Sherlock, but it happens. And you can choose how you want to handle that, right? So one way is to treat each recalled event individually and say that's a different event. I'm going to calculate its own correlation and put them separately into the matrix. Or you can treat each event you can make sure that there's going to be 50 events, basically. And so if a person returns to the same event multiple times, you just average across all of those returns. And you have, for the within subject analysis, you can treat returns to the same event separately, but if you're doing an across subject analysis, you're going to have to average in some way. So that's why we have these 2 different ones. And here we're comparing movie scenes directly between people, and here we're comparing recalled scenes directly between people. Okay, and we could look at them. So up here is the movie versus recall correlation matrix for the within subject analysis, and you can kind of see that diagonal there. It's not super strong though. It's not super strong visually. It is actually all positive though. So that's over here. Oh no, sorry, this is individual subjects. So this is the average diagonal value for each subject's correlation matrix. And this is the average correlation matrix across all subjects. Although the pattern analysis, the correlations are calculated within subject. Over here is the movie correlation between subjects for this ROI. And again, for each individual subject, the diagonal of that matrix. And then here's recall. And the reason you have this black line is there's one scene in the movie that is never recalled by anybody. And that's because, we have the 50 scenes, they're split into 2 scans, and at the beginning of each scan, there's a little introductory cartoon movie clip, which is not actually part of the Sherlock story. And 16 out of the 17 subjects did not bother to describe that part of the scan, but one person did. And so that person does have data, but she did not bother to describe it the second time it was presented. So there's no data there. That's the same thing up here. Okay, and then the last thing that I'll show is reading in this Excel file, right? So there isn't code in this tutorial that shows you how to do the encoding model, but we could talk about it if you want to try to implement it. It's just linear regression. But this this function reads the Excel file, at least so that you know you have your timing correct. So then you can easily match it to the brain data if you want to. Okay, and it makes this figure for you that I showed earlier. So the regressors are whether somebody is speaking, the number of people that are on the screen. These are at the 1,000 segment level, right? The encoding model is built at the scene level, so then you would collapse these values into the 50 scenes. But you could do regressions using these time courses if you want. Arousal valence, indoor, outdoor, music, written words, presence of other characters. Okay. Oh yeah, and it just, you can also tell it to plot just one and then look at, that's just a different visualization of the same thing. Okay, that's all I have. Any questions about this stuff? Anyone?
Do you handle motion differently for the recall, given that they're like actively speaking?
No. We instruct people to stay as still as they can and to speak using their mouth, not the skull. And we reject using the same threshold that we would for any study. So people definitely move a little more during recall than they do during the movie, but if they're over the voxel size, then we drop them. And it actually is not, I don't find it's that bad. But you know, that is, you want to be doing analyses where that could only add noise to your result. You don't ever want that to be the source of your result, right? So between run, like between movie and between movie and recall, and between subjects when they're all saying different things, you know, that's the source of noise. But if you were starting to do stuff with like temporal correlation during recall, then you would want to think hard about that. Yeah.
So Janice,